Welcome to today's lesson on Chapter 6.2, Some Difference in Double Angle Identities. Angle identities that we're going to look at today are more complicated than, say, the reciprocal identities or the Pythagorean identities that we've looked at. In order to derive those identities, we have this somewhat complicated drawing that we have here in the middle of the page. The drawing in the middle of the page is actually a combination of three right angle triangles that we're going to need. So I'll start with sort of the main triangle that we're looking at, and that's our triangle over here on the left. I've got triangle OBC, which is a right angle triangle. I can see that the angle that I have forming at angle O here, or angle BOC, is the sum of two other angles. I just don't happen to know what they are. Right? I have some sum of angles, or I can rewrite that angle O as alpha plus beta. Now, what I need to do in order to see how the angle identity works, our goal initially is we're going to come up with an expression for the sine of alpha plus beta. And we're going to rewrite it so that the sine of alpha plus beta can be rewritten in terms of just the sine of alpha or beta, or the cosine of alpha or beta. And the reason we would want to split an angle up into the sum of its parts is so that alpha and beta could be values from our unit circle. And then we would be able to take an angle and find the sine of some angle that's not on our unit circle as some sort of combination of angles we can find on our unit circle. So the first thing that we do is we're going to split that triangle up into two right angle triangles. And it's really important that they're right angle triangles. So this line that I'm drawing right now, or that I just drew, line OA, has to extend far enough so that the triangle OAB is a right triangle. And you can see that triangle drawn out over to the right side. It's this angle sort of at the top of our picture here in the middle, and I've just rotated it and just drawn out angle OAB so we can see that it's a right angle. From there, I will also just extend the line OC until I can drop a perpendicular from A down to it, and that gives me the triangle OAD. And I'm going to use these triangles to see what's happening in terms of this diagram, to be able to pull things together. I'm just going to take those out from our original diagram there for a second, to see what's going on in terms of how I can rewrite this identity. So we start in a very simple place. We know that the sine of any angle, like if I called that angle X, the sine of the angle is opposite over hypotenuse. And so I can see that the sine of alpha plus beta is going to be side length BC over side length OB. Okay, so now what we're going to do is I'm going to look at side length BC, and I'm going to see in the diagram that I have, I can actually split that up. I can split that up into BF plus FC. I can just, I'm going to draw that line AF in there, that just splits BC up into two parts. And so I can rewrite the sine of alpha plus beta. I will change the numerator, and I will change that numerator to BF plus FC. Okay, now both of those, of course, are still being divided by OB. All right, now I'm going to use our favorite little trick, and I'm going to multiply by 1. And I'll show you why I'm doing this in just a second. I need to multiply both of the first terms by BA. So I'm going to multiply by BA over BA. And then I'm going to multiply the FC over OB by OA over OA. Now I'm picking these for a particular reason that I will show you in just a second. I'm setting up new trig ratios for the smaller triangles. And so if I rewrite those fractions on the right side. Now I haven't changed them, right? I've only multiplied by 1, so I haven't changed them. I'm just changing what they look like. And I'm going to basically sort of swap numerators and denominators. We know that order doesn't matter. So I could rewrite that as BF over BA. The reason, of course, that I'm doing that is because there is one more right angle triangle in here that we can look at here in a second. And we'll come back to that in just one moment. Let's finish writing this out. That would leave me with BA over OB. And then we're going to have, sorry, there's a plus sign in there, FC over OA and OA over OB. Okay, so I've just sort of moved my numerators and denominators around a little bit in each of those terms that are being added together to give me something a little more useful. So let's start with our OA over our OB. So if I see OA over OB, the cosine of beta is OA over OB. Okay, if I then look at, let me see, if I do BA over, so BA over OB, that's going to give me the cosine, or sorry, the sine of beta is going to be BA over OB. And so that gives me that term and that term. All right, what I need to look at next is I need to do a little bit of geometry inside my diagram. So I'm going to just grab a highlighter here for a second. I'm going to look at an alternate interior angles theorem, or what we often call the Z theorem. And I can see that that angle is going to be angle A. And that's my angle right there. Because OA and AB meet at a right angle, that tells me that the angle in here is going to be 90 minus alpha, or its complement. AF is parallel to the ground, so that creates a right angle at angle F. And that means that if I subtract 90 from 90 minus alpha, or sorry, I subtract 90 minus alpha from 90, that's going to leave me with alpha here, because the angle FBA is a complement to angle FAB. So I can see that the angles in here have to be complements. So I now have another right angle triangle that we're going to look at. And we need this one to get our ratios. And so we're going to add that down here. So we've got B, A, F. We have alpha up there. So in this little triangle, I can see that I have, let's do cosine first. So cosine of alpha is going to be BF over BA. And so I can see that that's right there. And then if I did the sine of alpha, I get angle FA. Oh, what did we call it here? Hang on. Oh, right. We need to make one more little switch before we can do that. No, let's write down the sine of alpha. Alpha is going to be FA over BA. Okay, so last little switch that we have to do. I'm going to grab my highlighter again, but I'm going to change it to a green this time. Okay, so the last switch we have to do, we have our angles, or our side lengths in here in terms of FC But what I want to look at in that picture is that FC is equal to AD. And so I'm going to make a little switch in our formula here. And I'm going to change, I'm going to add a few things that I know, and then I'm going to change. Actually, I'll just leave all these ratios the same for now. We'll switch them on our next step. Times BA over OB. So I'm going to change FC, and we're going to let that be equal to AD, just because those are two congruent lines. So that gives me AD over OA times OA over OB. And now to that last triangle that we need to look at. We didn't actually need, we don't need that one. But it's there, that's okay. It's not going to hurt anybody. If I look at this middle triangle here, I can see that the sine of alpha is going to be AD over OA. So that gives me my last ratio that I needed to find in order to rewrite the sine of alpha plus beta. Okay, so BF over BA was my cosine of alpha. So that's going to be cosine of alpha. BA over OB, if I go up to the right, I can see is sine beta. AD over OA is what we just looked at. That's sine of alpha. And then our very last one, OA over AB, is cosine of beta. And that is our sum of angles identity. We have now successfully, just through a bunch of algebra and a little bit of geometry to find some equivalent angles, some similar triangles, and using some congruent sides, have used some algebra to rewrite the sine of alpha plus beta as the cosine of alpha times the sine of beta plus the sine of alpha times the cosine of beta. Now, you could check this if you wanted to with, I don't know, just pick any angle and then add two values together to give you that angle. And you could just throw some numerical examples in your calculator to prove to you that this actually works. Our next goal, and we're going to do this a little more compactly, I think we've got enough room here to do it, is to do the exact same idea, but with cosine. So we're going to do the cosine of alpha plus beta. We know that's going to be adjacent over hypotenuse. And the adjacent over hypotenuse for our O, let's just sketch over that a little smoother. For our OBC, we know cosine is going to be OC over OB, right? Our adjacent side over our hypotenuse side. So that's going to give me, let's take that OC. Now this time we got to be a little careful about how we do this. And this is one of those things where you do it because we know it works. It's not necessarily obvious before you see it, but we have to be able to follow it through and see where everything comes from. We're going to do something a little weird this time. We know that we want OC in there, but I can rewrite OC as OD minus CD. So I'm going to rewrite my OC as OD, it's still going to be over OB, minus CD. Okay, so then I'm going to do the same idea that we did before. We're going to multiply by specific side lengths by 1, right? So a side length over a side length in order to give us useful ratios in just a second. So I'm going to multiply the first one by OA over OA. And if you know what the ratio, or sorry, if you know what the identity looks like, you can make a couple of switches as you go, and you can see where these switches are going to come from. Now, I'm going to make one little switch here before I write down the next term. CD is exactly the same as FA. I'm going to need that little triangle again. I'll just write the alpha in there because we know that that angle is alpha. And so I'm going to switch CD for FA. So I'm going to get FA over OB, and I'm going to multiply this one by BA over BA. Okay, I'm just going to haul this up to the top over here. So I get the cosine of alpha plus beta. Again, I'm going to rearrange things. So I'm going to write that first term as OD over OA times OA over OB minus FA over BA times BA over OB. Okay, so now it's just a matter of finding those ratios in this triangle. So if I look at OD over OA, I can see that the cosine of alpha is OD over OA. My next one is OA over OB. So you have to look up to your beta triangle for that one. And you can see that the, what was it, OA? So OA is the adjacent side. So the cosine of beta is OA over OB. You can see we're switching back and forth between the alpha and the beta triangles. If I look in the small triangle, FA over BA is the sine of alpha over BA, and then we have BA over OB, and we can see that that is the sine of beta. So I'm just finding the right angle triangle in the diagram that corresponds to the algebra we did. So again, this is more of a showing that this works and how to do it, not I would expect you to be able to do this from scratch. And so I get that the cosine of alpha plus beta, so OD over OA is the cosine of alpha, OA over OB is the cosine of beta, and then we're subtracting, and I get the sine of alpha, and BA over OB is a sine of beta, and that is my sum of angle identity for my cosines. Now, if I want to come up with a difference of angles identities, I can use some of the properties that I know about trig functions. I'm going to draw a little quick unit circle for me here. If I just find any random rotation beta, and I look at negative beta, I can see that the cosines of those two things are equal. There's nothing I have to worry about. So if I wanted to do the cosine of alpha minus beta, well, any place I have the cos of negative beta show up, I can just replace that as the cosine of beta. If I look at our sines, and let's say, again, I just take some random angle beta, and I want to look at what happens for my sine with an angle of negative beta, we can see, of course, that I have a reflection over the x-axis, right? Those points are mirror images or reflection images over the x-axis. And what that means, of course, is that my y value changes. So the sine of negative beta is the same as negative sine of beta. So now we're going to look at the sum and difference identities using tangent. Now I'm actually just going to do the sum identity. We can use the same trick that we had just talked about to look at the difference identity by looking at what we know about how a tan of alpha is related to tan of negative alpha. And that's just, of course, going to be, if I draw a quick little unit circle here, if I have the tan of alpha here, and I look at the tan of negative alpha, I'm dividing, right, sine by cos, so a positive divided by a positive. Whereas if I do negative alpha, I'm going to have a negative divided by a positive. So I can see that the tan of negative alpha is equal to negative tan of alpha. So I can use that to look at my, my difference identity as well. So to do my sum identity with the tangent function, I'm going to use the sum of angles identities that we just looked at for both sine and cosine. So we know that the sine of alpha plus beta is sine alpha cos beta plus sine, or actually usually we tend to write it cos alpha sine beta. Now I believe those terms are in the opposite order as they were before, but we're just adding, so it doesn't really matter. And it doesn't matter how you write it down. Some people will do their sines first. And so you'd have like sine alpha cos beta and then sine beta cos alpha. But most of the time, I think, I don't even know that it's convention, but it's just sort of the normal way we approach it. People tend to do alphas and betas. You can do whatever you want. Cos of alpha plus beta is cos alpha cos beta minus sine alpha sine beta. Okay, so what I'm going to do now is I'm going to divide both the numerator and the denominator by cos alpha over cos beta. And I'm doing that, I'm still really multiplying by 1. It's just that the thing that I'm multiplying by is 1 over cos alpha cos beta. And I can see that when I multiply that first term in the denominator, I'm going to get something to cancel for me. All right, so let's write everything out to see exactly what we have in terms of each of our fractions here. So I'll have sine alpha cos beta all over cos alpha cos beta plus cos alpha sine beta all over cos alpha cos beta. Okay, so that's my numerator. And then my denominator, I'm going to have 1 for my first term. I'm going to write it down. I'm going to have cos alpha cos beta over cos alpha cos beta minus sine alpha sine beta over cos alpha, cos beta. Okay, and the other thing that's really important to point out again here, this is not something that I would expect you to look at and understand what to multiply by. The reason I'm multiplying by 1 over cos alpha cos beta in my numerator and denominator is because I'm trying to simplify this to get a whole bunch of tans to fall out is what's going to happen. This is, once you've seen it, you should be able to follow it through. You could understand or memorize what we were going to do if I were ever to ask you to derive this, which I'm not going to. But it's not that we're looking for anything sort of big here in terms of getting things. It's not like there's a problem-solving piece that's coming into this to understand where this derivation is coming from. I'm doing the derivation and I'm showing you this works. I'm showing you where all these angle identities come from. And the nice thing about this is it's really just a little bit of algebra and a little bit of geometry. So it's not anything super, super complicated. Okay, so if you look at everything I canceled every place we had something divided by itself, so any place where we had a value equal to 1. And now I've got a whole bunch of sines over coses, and each time I have a sine over cos, we know that sine over cos is tan. So now I have that the tan of alpha plus beta is going to be the tan of alpha plus the tan of beta. That's all that's left of my numerator. In my denominator, I have 1 minus the tan of alpha times the tan of beta. And that is my sum of angles identity for tangent function. Okay, so let's take a look at some double angles. So double angles are very easy to come up with algebraically, because all we're going to do is we're going to rewrite the sine of 2 theta as the sine of theta plus theta. So that gives me that the sine of 2 theta, so I'll go back and again I use my sum of angles identity, and that's going to give me sine theta cos theta plus sine theta cos theta. I guess usually we would, I'll rewrite this one. Given the way our identity is written on our sheet, we would probably write that as cos theta sine theta, but we can see those are the exact same thing. If you're wondering why we have switched to thetas instead of alphas and betas, is because we only have one angle that we have to worry about with these double angle identities. And so that's normally why they're written in terms of theta. I could have just as easily stuck with alpha or beta, but I only need one angle here. Well, so I have something plus itself, and that means I have two of those things. So I have 2 sine theta cos theta, and there is my double angle identity for sine. Those of you who are in Physics 12 have seen this identity as well, because we've needed that in a couple of our, well, I guess just in one of our derivations so far. All right, when it comes to the double angle identities for cosine, if you've looked at your formula sheet, you'll see that there are 3 formulas, or there are 3 identities we can use. So my first one, if I use my cos alpha cos beta minus sine alpha sine beta, we can see that I get cos theta times cos theta minus sine theta times sine theta, which of course would just give me cos squared theta minus sine squared theta. So that is one of them. That's probably the most common one that we'll use, but not necessarily. I'm going to make a little substitution from our, let's start just with our basic Pythagorean identity. I could rearrange that in terms of sine squared, and that would be 1 minus cos squared, or I could rearrange that in terms of cos squared, and cos squared would be equal to, cos squared theta would be equal to 1 minus sine squared theta. I'm going to use that first one, and I'm going to substitute for my cos squared. And so what that will give me, I could then have that the cos of 2 theta is 1 minus sine squared, right? That's my cos squared, minus sine squared. So that gives me cos of 2 theta is 1 minus 2 sine squared theta. And so that's our double angle identity for cosine, written entirely in terms of sine. And then my other option, of course, would be if I did the exact same thing, but instead replaced for my sine squared. And so I'd have cos of 2 theta is equal to cos squared theta minus 1 minus cos squared theta. So we're subtracting a negative there, and when I simplify, that'll give me my final version. So I've got a cos squared theta plus cos squared theta, so that gives me 2 cos squared theta minus 1, and that is my third version of the double angle identity for cosine. Okay, so let's move on and take a look at, just one moment here. Two more examples for us to look at. We're going to start by finding the exact value of the sine of 75 degrees. So we're going to move to degrees for a while because almost all of our examples we've looked at are radians, but we should do a couple in degrees every once in a while. So this example is going to show us how our angle identities are helpful for finding exact values for points that are not on the unit circle. And so what I need to think about is splitting up 75 degrees into two angles that I could find on the unit circle. And hopefully we'll see sort of right away that I could rewrite 75 as a sum of 45 and 30. Okay, so that tells me then that the sine of 75 degrees, I'll use my sum of angle identity for sine. And so that's going to give me sine of 45 cos of 30 plus cos of 45 sine of 30. So when I think about my unit circle, there's really only two places on the unit circle I care about right now. At 45 degrees, my coordinates are root 2 over 2 and root 2 over 2. At 30 degrees, my coordinates are root 3 over 2 and 1/2. So now I can evaluate using the unit circle because I've written the right-hand side in terms of values I know. So sine of 45 is root 2 over 2. Cosine of 30 is root 3 over 2. Cos of 45 is root 2 over 2. Sine of 30 is 1/2. So that's going to get me, so I get root 6 over 4 plus root 2 over 4. And we would haul that together over one denominator, and I would write it as root 6 plus root 2 over 4. I guess if we wanted to, we could factor out a root 2 from there, but that's probably not something we would normally do. Now, this is a case where we can always jump to our calculator and we can check our answer in our calculator if we want to at this point. So if we haul up the calculator, we could do the sine of 75, and we can see, I'm just checking to make sure I was in, sorry, that I was in degree mode, which I wasn't. So let's try that again, sine of 75. And then if I do the square root of 6 plus the square root of 2 all over 4, and we can see that numerically those are identical. Okay, so let's take a look at example number 2. So example number 2 is going to be sort of follow the same general pattern that we're going to look at a lot over the next little while, where we're given an expression and asked to simplify it, and then we'll move on and we'll work on actual proofs. We'll still be following this exact same thing. I have to simplify the expression and I have to find the non-permissible values. Let's start with my non-permissible values. Non-permissible values. That will happen when the cos of 2x plus 1 is equal to 0. Okay, so I can start to solve for this. I get the cos of 2x is equal to -1. If I take the inverse cosine, we know that's going to happen at, or the inverse cosine of 1 is at pi, and I'm doing a general solution here because I want to find all of those non-permissible values, and so that I get for my non-permissible values that it's when x is pi over 2 plus pi k kei. Okay, so those are my non-permissible values. Now I can go off and I can work on the solution to simplifying this expression. I'm normally going to do non-permissible values first because if we don't, we tend to forget them when we're working our way through. All right, so I don't have a choice when it comes to the sine of 2x. I know that that's going to be 2 sine x cos x. But when it comes to using the cosine of 2x, I have 3 choices in terms of what am I going to do to simplify things. There's not ever really a right or a wrong answer, but sometimes it means we have to go through multiple steps to be able to get things to simplify. So the big thing that I notice when I look at this question is that I have a +1 in that denominator. And if I use the second identity, I'm going to cancel out that +1 and only give me one product of terms in the denominator, which will allow me to start to cancel terms. So for my cos of 2x, I'm going to use 2 cosine squared of x minus 1. So that's the identity I've used. And then I still have that +1 in the denominator. Okay, so I get the 1's are going to cancel, and I get a 2 cos squared x. I can now start canceling common factors in the numerator and the denominator. And I can see that I'm left with sine of x over cos of x, which of course is tangent. Now I'm going to make a final statement. So what we've just shown is that the sine of 2x over the cosine of 2x plus 1 is equal to the tangent of x, but x is not equal to pi over 2 plus pi k kei. So that identity is true at every point except for pi over 2 plus pi k. All right, that's it for our lesson today. Make sure you have any questions about anything that we've gone over today ready for our next class. These are the kinds of things that you might have to sit down with and take a look, maybe 2 or 3 times through either the derivations or the examples to make sure things are making sense. Good luck.